What if I told you that the force holding the entire universe together is something we don't actually understand? Not fully. Not even close. And here's the twist, neither did Isaac Newton, the man who discovered it. In fact, one of the greatest physicists ever, Richard Feynman, once said something shocking: nobody really understands gravity. So, what's going on here? How can something so familiar, so obvious, be such a deep mystery? Let's start with something simple. You drop your phone. It falls. You don't question it. Gravity pulls it down. End of story, right? But if you pause for just a second and ask, why does it fall, things get weird, fast. Newton asked that exact question. Legend says he saw an apple fall from a tree and wondered why it didn't just float sideways or drift upward. What he realized was groundbreaking: the same force pulling that apple down is also pulling the moon toward the Earth. In other words, gravity isn't just something that happens here, it's universal. That idea alone changed everything. Suddenly, the heavens and Earth were governed by the same rules. Planets orbit the Sun because gravity is pulling them in. The Moon orbits Earth for the same reason. It was elegant, powerful, and incredibly accurate. Newton even wrote down equations that could predict exactly how objects move under gravity. But here's the part most people don't realize: Newton himself didn't know what gravity actually is. He could describe what it does with stunning precision, but when it came to explaining how it works, he admitted he had no answer. Think about that for a second. Imagine you invent a formula that predicts exactly how a ball will fall, how a planet will move, even how comets travel across the sky, but when someone asks, okay, but what is this force, you just shrug. Newton called it action at a distance. Objects somehow pulling on each other across empty space, instantly. No wires. No contact. Just influence. Even he felt uncomfortable with that idea. And honestly, it is kind of strange. How does the Earth know the Moon is there? How does it reach across space and pull it? There's no visible connection. No rope. No signal you can see. For over 200 years, scientists used Newton's gravity because it worked. It predicted things perfectly. But deep down, that question lingered: what is really causing this force? Then came Albert Einstein, and he turned everything upside down. Einstein didn't think of gravity as a force at all. Instead, he imagined space itself as something flexible, like a fabric. Picture a stretched rubber sheet. Now place a heavy bowling ball in the center. The sheet bends. If you roll a marble nearby, it doesn't move in a straight line anymore. It curves toward the bowling ball. According to Einstein, that's what gravity really is. Massive objects like Earth and the Sun bend the fabric of space and time, and everything else simply follows those curves. So when you drop your phone, it's not being pulled down by an invisible force. It's actually moving along a curved path in a warped space. Sounds wild, right? But it gets even stranger. In Einstein's view, gravity isn't something reaching out and grabbing objects. It's the shape of reality itself. Space and time are not just empty backgrounds, they are active players, constantly bending and shifting. This idea, called general relativity, has been tested again and again, and it works. It explains things Newton's theory couldn't, like why Mercury's orbit shifts slightly over time. It even predicted black holes, objects so massive that they bend space so extremely that not even light can escape. And yet, even Einstein's theory doesn't fully solve the mystery. Because when you zoom into the smallest scales, the world of atoms and particles, gravity stops making sense again. In the quantum world, everything is described by probabilities and tiny interactions. Forces are carried by particles. Electromagnetism has photons. The strong force has gluons. The weak force has W and Z bosons. So naturally, scientists expected gravity to have its own particle too, called the graviton. But here's the problem: we've never seen it. Not once. And our current theories can't fully explain how gravity fits into the quantum world. It's like having two perfectly working systems that refuse to talk to each other. On one side, Einstein's smooth, curved spacetime. On the other, quantum mechanics with its jittery, unpredictable particles. Both are incredibly successful, but they don't agree. And gravity sits right in the middle of this conflict. This is why Feynman said what he said. Not because scientists are clueless, but because the deeper you go, the more gravity slips through your fingers. Let me give you a thought experiment. Imagine you're floating in deep space, far from any planets or stars. You feel weightless. Now suddenly, you're inside a closed box and the floor starts pushing up against your feet. You feel heavy again. Are you standing on Earth? Or is the box accelerating upward in space? Here's the crazy part, you can't tell the difference. This is one of Einstein's key insights. Gravity and acceleration are fundamentally linked. The feeling of weight might not be a force at all, it might just be the result of how you're moving through spacetime. So now gravity isn't just a force, or even just curvature. It's tied to motion, perspective, and the very structure of reality. And still, we don't fully understand it. We can detect gravitational waves, ripples in spacetime caused by massive events like black holes colliding. We've literally heard the universe shake. But knowing that these ripples exist doesn't mean we understand the deeper mechanism behind them. It's like hearing thunder without fully understanding what lightning is. Even more mind-blowing, gravity is incredibly weak compared to other forces. A small magnet can lift a paperclip against the entire pull of the Earth. That means electromagnetism is vastly stronger than gravity. So why does gravity dominate at large scales? Why does it shape galaxies, stars, and the universe itself? That's another unanswered question. And then there's dark matter and dark energy, mysterious components that make up most of the universe. We can't see them, but we know they're there because of how gravity behaves on cosmic scales. Galaxies spin faster than they should. The universe is expanding faster than expected. Something is affecting gravity, or maybe our understanding of gravity itself is incomplete. So where does that leave us? We have Newton's incredibly accurate predictions, Einstein's elegant geometric explanation, quantum theory's powerful framework for the microscopic world. And yet, when it comes to gravity, something is still missing. It's like we're reading a book where every chapter makes sense, but the overall story doesn't quite fit together. And that's what makes gravity so fascinating. It's not just the force that keeps your feet on the ground. It's a doorway into some of the deepest questions in physics. Questions about space, time, reality, and how everything connects. So the next time you drop something and watch it fall, remember, you're witnessing one of the greatest mysteries in the universe. Not just a simple force, but a puzzle that has challenged the smartest minds for centuries. Newton described it. Einstein reimagined it. Feynman questioned it. And we're still trying to understand it. If that doesn't make you look at the world a little differently, I don't know what will. If you enjoyed this and want more mind-bending ideas explained simply, hit like, subscribe, and let me know in the comments what topic we should explore next. Because sometimes, the most familiar things hide the deepest secrets.